Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Monday, December 7th, 2020. December 7th, Pearl Harbor Day. Now, I'm not that old, but of course, that's the day that the Japanese Army bombed our base at Pearl Harbor in Hawaii, which then pulled us into World War II. My grandfather served in World War II. He was not at Pearl Harbor when the attack happened, but he was on active duty, and he was sent there soon thereafter for that. So I've got a lot of memories growing up of my grandfather telling me about all that. So anyway, in remembrance to all those who served in World War II, and also, of course, in all the wars since, and those who are on active duty right now. Again, I thank you for your service. So, again, with this being Monday the 7th, this is actually also our last full week of school prior to finals. So we got a lot to get done this week as we finish up this semester, and so we're going to get right to it here in just a second. I believe this is also, if I'm not mistaken, let me look here, let me double check, our 74th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do now and see what the schedule is for today. So today we're going to get going on equation balancing and writing. We're right where we need to be in regards to that. Your homework for today was to complete the Unit 6-2 assignment number 1, which you picked up Friday, along with the symbols handout and, of course, the gigantic notes packet. I failed to mention that Friday, but I'm sure you all noticed how thick it was. But anyway, so we got a lot to do in there. Anyway, that assignment, Unit 6-2 assignment 1, is due now. And I am collecting it for a grade, as I told you Friday. So if you're here in class, that should already be on my desk. If you are at home, then you need to be submitting that to me electronically during your regularly scheduled class period. So don't be late. All right. Of course, you can check the answers, your answers before you do that. If you're here in school, of course, they're on the back board. If you're at home, they will be posted on the answer keys page in Canvas in time for you to do that. So let's move on. Hang on and pay attention. Yes, that's good advice. Everything we have done to this point this semester has been to get us ready for the real thing, and that is chemical reactions. And not only that, but what they do for us. I mentioned this Friday in our little introductory video over this unit that, learning how to write and balance and classify reactions is one thing. But then what do we use them for? That's the real important thing, and that's what we're going to spend most of the second semester doing, is what chemistry does for us today in today's society. So this is a unit of major importance that will carry us through not only the rest of this semester, but the rest of the school year. And as I mentioned a little bit ago, it is a monster. Notice the thickness of the notes packet. We will not finish this entire packet before the end of the semester. Like I said, we only got a week to go. But we're going to get a pretty good start on it, and then we'll pick up with that where we left off when we return in January. So, having said all that, let me pull up the notes, and let's get going on today's lesson. Okay, so we ended Friday right here with types of chemical equations. A little introduction on what equations are, what reactions are, and now we're going to get right into the thick of it right now. So basically, we have three basic types of equations. The first one is called a word equation. You're going to be dealing with these some of these on your assignment for tomorrow, not only tomorrow, but for the rest of the unit. In a word equation, only words are used. No chemical formulas are used. No numbers are used to show the ratio by which all substances react. So here we're showing we have the element iron reacting with the element oxygen and forming the compound iron 3 oxide, which is actually commonly called rust. All right. So this is basically a word equation that describes the chemical reaction, but that's all it does. That's all it does. In a skeleton equation, our second type, the correct chemical formulas and states of matter are written, but no numbers are used to indicate the ratio by which all substances react. Okay? And so now that iron then translates to Fe. Fe, of course, is iron is a monatomic element. Its representative particle is a single atom. So here we have Fe, and then iron, of course, is in the solid phase. We looked at those symbols used in equations on Friday, and we're going to start using them today. So Fe is a solid. Oxygen now is a diatomic element. Remember Hopple fiber. All right, so there are 7 elements that are in a diatomic state, meaning they're 2 atoms bonded together into a 2-atom molecule. Oxygen is one of those. So, and O2, of course, is a gas at standard conditions of temperature and pressure. And then the formula for iron 3 oxide. Well, here's where you got to know your nomenclature, all right? How to write a formula. We spent the whole last unit working on that. And so iron 3 oxide is Fe2O3, and of course we know that is a solid as well, okay? So this is the skeleton equation. Note that the number of each atom on both sides of the equation is not the same. This equation is not balanced. Well, here we have 1 Fe on the left, but there's 2 on the right. Here we have 2 atoms of O on the left and 3 on the right. It's not balanced, all right? So we're not done with it yet. Let me advance the page here. So I want to make note, put a big star by this, all right? Big star, all right? That you need to know, starting today, the normal states of matter for most all elements and compounds. And again, normal state of matter, again, is under conditions of standard temperature and pressure, whereby, room conditions, conditions you would see inside or even outside if the temperatures aren't too extreme, or in a factory or production facility where these equations are going to be run, or a lab. And so at standard conditions, right? Normal operating conditions. Most elements, so we're going to start with elements. Most elements, 90+% of them, are solids at room temp and standard pressure. Solid, including one of the diatomic elements, iodine. All right. So nearly all of your monatomic elements, with the exception of the noble gases, of course, and there's a couple that are liquids, not many, are solids at room temperature, including I2. All right. Mercury and bromine, Hg. Bromine, of course, is a diatomic element. Mercury and bromine, Hg and Br2, are liquid at standard conditions of temperature and pressure. And the rest of the diatomic elements, which I listed here as honkulf, all right, I left the Iber off, just honkulf, hydrogen, oxygen, nitrogen, chlorine, and fluorine, as well as the noble gases, are gases at standard conditions of temperature and pressure. So we have 5 of the diatomics, and of the noble gases, which total 7, that's 12 gases, all right, 12 gases at standard conditions, 2 liquids, so that's 14 out of 118, all right? The other 114 elements are solids, all right? Don't forget that, all right? Now, compounds. Unless they are dissolved in water, meaning they're in solution. Remember that we learned that term is AQ, aqueous or aqueous, depending on how you like to pronounce it. I've seen both. All ionic, so unless they're dissolved in water, then all ionic compounds are solids, right? Remember how strongly bonded ionic compounds are? Ionic bonding is very, very strong. And so it pulls the particles very, very close together. Hence, they're solid, all right? Nearly all molecular compounds are gases. Exception, water. Well, water's got hydrogen bonding as an intermolecular force, Which pulls its particles much closer together than normal. Of course, water can be a gas, water vapor, steam, etc. But under normal conditions, of course, of temperature and pressure, we all know that water is a liquid. Thank goodness it is. And also, SiO2, silicon dioxide, is a solid, all right? So, all ionic compounds, unless they're dissolved in water, are solids. All molecular compounds, with the exception of water and SiO2, are gases, all right? And acids, the last one, are in solution. Acids are all dissolved in water. They're either a gas or a solid. Normally, most of them are gases because they're molecular and but they're dissolved in water, and so they are aqueous. All right. So remember these states of matter rules. All right. It is something starting today you absolutely have to know. All right. So add that to your list of stuff you had to memorize. Okay. All right, let's go to the next page. Our third type of equation now we're getting to the meat of it, is a balanced equation. In a balanced equation, each side of the equation has the same number of each atom. This is done by using whole numbers placed in front of each substance. These numbers are called coefficients. Okay, coefficients are not the same as subscripts. All right, subscripts are the little numbers found within a formula that shows how many of each atom or ion it makes up one molecule or one formula unit of that compound. All right, these are coefficients. These are numbers placed out in front of something, whether an element or compound, either one, in order to balance the equation. So now that skeleton equation we are showing here is balanced. All right, 4Fe solid plus 3O2 gas yields 2 Fe2O3 solid. So if you notice now, we have 4 Fe's on the left and 2 times 2 or 4 Fe's on the right. We have 3 times 2, 6 O's on the left, and 2 times 3, 6 O's on the right. Anything that's follows behind a coefficient is multiplied by that coefficient. All right. So why do we have to balance an equation? Why? All right. Well, we got a pretty good reason why. A balanced chemical equation follows the law of conservation of mass. And we have seen and we have proven ourselves and we have demonstrated countless times that regardless of the type of change, whether it be a physical change, a chemical change, a nuclear change, whatever, that the conservation of mass applies. All right? Mass is neither created nor destroyed in a chemical reaction. It's always conserved. This is why we balance an equation. So let me demonstrate that with this one right here. All right. So let's first take a look at the molar mass of each of these substances. All right. The molar mass, how many grams there are in 1 mole. All right. So Fe, if you look up Fe's average atomic mass, which is the same number we use for its molar mass, it's 56 grams per mole. O2, well, O is 16 times 2 is 32 grams per mole. And Fe2O3, so we have 2 Fe's, which would be 112, 3 O's, which would be 48, 160 grams per mole. All right? Well, doesn't take a math genius to figure out that 56 and 32 does not add up to 160. All right? Well, here's why we balance the equation, all right? The balancing coefficients are the moles of each substance involved in the reaction. Moles, all right? So 4 moles of iron plus 3 moles of O2 yields 2 moles of Fe2O3. This is the mass in grams of 1 mole. That's what molar mass is. So if we take for iron 4 moles times 56 grams per mole, all right, we get a mass of 224 grams. If we take 3 moles of O2 times 32 grams per mole, we get 96 grams. And if we take 2 moles of Fe2O3 times 160 grams in a mole, we get 320 grams. Take a look now. 224 plus 96 is 320. And over on the right, 320. All right? Conservation of mass. All right? The only way a chemical equation on paper, written down, of course, follows the conservation of mass is when the equation is balanced. All right? So, the equation must be balanced. All right? It must be balanced. Got to. All right? When these two things react to form iron 3 oxide, they do so in a 4:3 ratio and then produce 2 moles of iron 3 oxide. Now, that doesn't mean you have to react 224 grams with 96 grams to get 320. You can do any quantity you want, but it's going to be in that same ratio of 4 moles to 3 moles to 2 moles. All right, same ratio. Okay? All right, so let's get to procedure. Now we know why we balance an equation. Let's look at how to do it. And I know you've done this before. I'm sure of it. I know you did it in Chem 1. And even if you weren't in Chem 1, those of you in honors who are going to get this lesson eventually, you've been balancing equations probably since the 7th or the 8th grade, I'm guessing. I'm pretty sure you have. Now, we're going to see some procedures as to how to do that, and maybe how to save you a little time too. So here's the procedure. Number 1, make sure the formulas are correct. Okay, so if the equation's written for you, that's one thing. That's nice and easy, all right? Well, what if it's not? What if it's a word equation that you have to write it yourself? Well, here you go. You got to know nomenclature in order to do that, all right? All of a sudden, it becomes not as easy, all right? So make sure that the formulas are all correct, and make sure that the substances are on the correct side of the equation. Make sure that the correct state of matter is listed for each substance that we just talked about a few minutes ago, all right? A lot more to it now, all right? Next, count the number of atoms of each element on each side of the equation to see what needs to be balanced. Now, I put a little note here. Sometimes the skeleton equation is already balanced, meaning that everything combines in a 1 to 1 to 1 to 1 or whatever ratio. It doesn't happen very often, but it does happen, all right? Next page, third, balance each atom using the smallest whole number coefficient. That again, the coefficients are placed in front of each substance, all right? They're not subscripts, all right? They're coefficients, different. 4, shortcuts, okay? If you have a polyatomic ion on both sides of the equation, you can treat that ion as one thing, as one unit, rather than balancing each atom separately. So here's an example of that. Let me show you what I mean by that. So here we have an equation here, HNO3AQ plus CaCl2AQ, so those are in solution, forms CaNO32AQ and HClAQ. All right, well, take a look here. We have the nitrate ion, NO3 minus 1, on both sides of the equation. Rather than balancing the N and the O's separately, we can balance NO3 as one unit, all right? So let's look at that. So here we have NO3. Over here we have NO3 in parentheses with a 2 outside of it, which means that there are 2 NO3s. So if I have 2 NO3s on the right, I can make 2 NO3s on the left by putting the coefficient 2 in front of HNO3, because remember, everything behind that 2 is multiplied by 2. So now NO3 is balanced. Well, now we also have 2 H's from placing that 2 there, which means we're going to have to put a 2 in front of HCl so we have 2 H's over there, which then also means we have 2 Cl's And if you look back over here, we already have two Cls. And the last thing is we have a Ca on the left and a Ca on the right. Balance. Balance. Okay. Here's another shortcut. If you have an odd number of one atom on one side of the equation, but an even number of that same atom on the other side of the equation, try multiplying the odd numbered one by 2. All right, so here's what I mean by that. So here we have S solid plus O2 gas yields SO3 gas. All right. Sulfur, of course, is a solid, as most elements are. O2 is a diatomic element. It's also a gas. SO3 is a molecular compound. What do we say about them? Nearly all of them, gases. All right. So we have one S on both sides. That looks good. But here, two O's on the left and 3 on the right. Well, if we put a 2 in front of SO3, that's going to turn that odd number of O's into an even number of O's, which is now 2 times 3, or 6. Which then means if we put a 3 in front of the O2, we now have 6 O's on the left side as well. Also remember, though, that by putting a 2 here, we also have 2 S's. And so we're going to have to put a 2 in front of the S on there as well. All right? So a couple little tidbits to save you some time there, some shortcuts. Step 5, double check the equation to make sure everything's balanced. We've been doing that as we go along. You need to do that every single time. Doesn't take but a few seconds. Number 6, make sure all elements are in the lowest whole number ratio possible. Let me explain that. So let me write this down and we'll take a look at it. So this is the same equation we just balanced up here. But now I have 4S plus 6O2 yields 4SO3. So my first question is it balanced? Is it? 4S is there, 4 there. 6 times 2, 12 O's there. 4 times 3, 12 O's there. Yes, it is balanced. But then the final question is, are those coefficients in the lowest whole number ratio possible? And the answer is no. All right. This can reduce. You can divide all the coefficients by 2. And that is what you would need to do. And so then we end up with what we had up here. All right. Double check that last thing before you move on to the next one. Are all the coefficients in the lowest whole number ratio possible? Okay. All right. So let's do some examples here, and then we'll send you on your way to do your assignment. So this first batch, these are the easy ones. These are the 7th grade ones, all right? The ones where the equations are already written for you. Well, maybe they're not the 7th grade ones. These are maybe the 10th grade ones, or the 9th grade ones, or the 8th grade ones, because we still got to do state of matter, all right? So we'll do that first. So N2, nitrogen is a gas. Forgot what's what. You need to really look that over and study, all right? Hydrogen is also a gas. And now here we have NH3, which is commonly called ammonia, all right? What kind of compound is NH3? It's molecular, all right? Covalent bonding. What do we say about nearly all molecular compounds? They are gases at standard conditions of temperature and pressure. You need to remember that, all right? Okay, so let's balance it. 2 N's there and 1 there, all right? It's an easy fix. Put a 2 there. 2 times 3 is 6 hydrogens. What's going to have to go in front of the H2? 3. And that makes that 6, and that one's done. Okay? Next one, SO3, another molecular compound, gas. H2O, of course, is a liquid. I would hope you'd remember that one. And notice over here, this is H2SO4. This is sulfuric acid. I went ahead and wrote that in for you. I don't really know why, because we said all acids are solutions. AQ, aqueous, or aqueous. Went ahead and did it for you. Not sure why. All right, so let's look at balancing this one. S there, S there. Good. 3 O's and another O in water makes 4 O's all together. 4 O's over there. 2 hydrogen, 2 hydrogen. Looks like everything's already balanced. This is one of those ones I was telling you about where everything is, the skeleton equation is already balanced, meaning technically these are all ones, but we don't use ones in equations. Make yourself a note about that. No ones. All right. Just the formula tells you there's one of them. All right. So what we do to then finish that off is just write balanced out there, which then tells us they're all ones. All right, without writing them all down. Okay. Next one, sodium is a solid. FeCl3, we're showing here that these two are solutions, probably because we wouldn't have known that otherwise. In a word equation we would have, but in a skeleton, a written one out, we wouldn't have. And then Fe over here, of course, is a solid as well. So it looks like Na is good for now, Fe is good for now, but here we have 3 Cl's, over here only 1. So we're going to have to put a 3 out in front of NaCl in order to have 3 Cl's, but that also means we have 3 Nas. So we're going to have to put a 3 Na over there. So basically this balance thing is just going to go back and forth, do the left, do the right, blah, 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 blah. I mean, that's really all there is to it. All right. Let's look at this last one here. CH4 gas. Well, CH4. Remember that one, folks? That's from the organic unit. That would be methane. All right. And remember, I put a gas here, but you should know that. We talked about that in that unit. Remember the alkanes, the ones that we all use for combustion reactions? We burn to produce energy. Remember the lowest molar mass to alkanes, 1 to 4, were gases. C1 through C4 gases, C5 to C10 liquids, and beyond 10 solids. You remember that. It's part of your nomenclature, right? I did it for you, but don't expect that on the homework or the test. These are all here. I don't know why I put them all here. Well, maybe I do know why. O2, of course, a gas. CO2 is a gas. Here's the one we need to talk about. We said H2O is normally a liquid at standard conditions of temperature and pressure. However, this is a combustion reaction. We're going to get into a much more detail here in the next day or so. In a combustion reaction, right? In a combustion reaction, we take a hydrocarbon and ignite it in the presence of oxygen. It burns. It produces CO2 and H2O gases. The reason it produces water as a gas and not a liquid is because it's hot. Right? This reaction is very exothermic. It gives off a lot of heat. That's what we use them for. Right? We burn hydrocarbons as fuels to produce heat. All right? And so there's a lot of heat being produced by this reaction. So much so, in fact, that the water transforms to water vapor. All right? And so H2O in a combustion reaction is a gas, not a liquid. All right? Because of how exothermic the reaction is, how much heat it gives off. Okay? Don't forget that. So water is almost always a liquid, except in a reaction like this, where you take a hydrocarbon in the presence of oxygen, you set it on fire, and then it burns on its own and produces CO2 and H2O gases and lots of heat energy. Okay? All right. Balance it. C there, that looks good. 4 H's there and 2 over here. I'll put a 2 there. So now let's add up the O's. We got 2 O's in CO2 and another 2 O's in those 2 waters. So that's 4 O's altogether. 2 over here with O2. Gonna need a 2 there. Okay? Gonna need a 2 there. We good? All right, so now let's look at some word equations. Here's where it gets a little tougher. All right? Let's look at some word equations. We have to get our thinking caps back on. Dig through the memory there, folks, and get back to nomenclature. All right, nomenclature, naming and formula writing. Okay, so let's look at the first one here. Carbonic acid solution. Well, acids are solutions. That was just a little hint. All right, carbonic acid. Carbonic acid. Okay, acids all have hydrogen ions in them. And then carbonic means the carbonate ion is in there, which is CO3 negative 2, which means we're going to need 2 hydrogens. So it'll be H2CO3. And it is AQ. It's a solution. All right? It says it right there, but we need to know that anyway. Produces carbon dioxide. Should know that one. CO2. And it is a gas. All right? Plus water. Now, water is a liquid. This is not a combustion reaction. All right? This is not a hydrocarbon plus O2 ignited. This is just another type of reaction. Water is going to be in its normal state, liquid. So there's our skeleton equation. So let's see. 2 hydrogens, 1 C, 1 C. 3 O's there, 2 there, 1 there is 3. Already balanced. Just write balanced out there to the side. Remember, we don't write ones in front of everything. Okay? Phosphorus. Phosphorus is an element. It's a monatomic element. It's not P2, it's just P. And it, of course, is a solid. Oxygen is also an element, but oxygen is a diatomic element. So it's O2. Don't forget that. What state of matter? Gas. Diphosphorus pentaoxide. All right? Well, it's got the prefixes to tell us what it is, P2O5. And again, this is a molecular compound. And remember, almost all of them are gases. So there's our skeleton equation. Got 1 P here and 2 here. So it looks like we put a 2 here. But then we run into a problem. Oh, 2 O's there and 5 there. That's that odd situation we talked about a little bit ago. So how do we get that O5 even? Well, we put a 2 as a coefficient out in front of there. And now instead of 5 O's, we have 10. All right? And so that would then lead us to put a 5 in front of the O2. So we have 10 O's there. But now look here. We have 2P2, which is 4 P's. That 2 has got to change to a full. All right? So there's that one. Sodium phosphate solution. All right? Sodium phosphate is Na plus 1. Phosphate, what's phosphate? Come on, guys. What is it? PO4 negative 3. So sodium phosphate is going to need 3 sodiums. Na3PO4. Solution, AQ. Calcium sulfate. Calcium plus 2. Sulfate, SO4 minus 2. So those are balanced. CaSO4. Solution, AQ. Yields, calcium phosphate. Okay, well, calcium's plus 3, calcium's plus 2, phosphate's negative 3. So that would be Ca3PO4 parentheses 2. Right? Remember your nomenclature. Doesn't say it's a solution. What is it? Well, calcium phosphate is an ionic compound. Ionic. Unless they're dissolved in water, which apparently this one isn't, that means it is a solid. The other product, sodium sulfate solution. Sodium's plus 1, sulfate's minus 2, which would be Na2SO4 solution, AQ. That's a big equation. We got the skeleton equation, now we got to balance it. You're thinking, wow, there's a lot to do with this one. Actually, not as much as you might think, because we got polyatomic ions in here. Let's start with this one. Here we have a PO4, phosphate. Here we have a PO4 twice, all right? So if we put a 2 in front of here, we now have 2 PO4s on the left to match our 2 PO4s on the right. So that takes care of that one. It's real easy to do that. You know, balance those polyatomic ions as a single unit rather than separating them. A whole lot faster. Well, that gives us 6 NAs though, so I think we better come over here and put a 3 in front of Na2SO4, which then gives us 6 NAs over there. Ca, here we have Ca3. Well, we're going to need a 3 there, all right, to take care of that Ca. So now what's left? Well, we still have sulfate, SO4. Well, here we have an SO4, but there's a 3 out in front, so that means there's 3 SO4s, okay? Over here we have an SO4 as well, but we got a 3 out in front of that. That means we got 3 SO4s over there. Done. Done. This one's done. All right. Last one. Butane. Butane, that's an alkane. That's an organic compound, a hydrocarbon. Bute means what? 4. Butane is an alkane. Remember C to the N, H to the 2N plus 2. C4H10. All right. Remember, organically, it's CH3, CH2, CH2, CH3. Right. But when we write it in an equation, we just use the regular form. Okay, shorter one. What state of matter is butane? Well, again, this goes back to the alkanes. Remember the alkanes? Just talked about this a few minutes ago. C1 through C4 are gases. C5 through C10 are liquids. And C11 plus are solid. So butane is a gas. You're thinking, now wait a minute. We got some butane lighters in our house. You know, most people do. Lighting candles or grills or whatnot. All right. Oh, cigarettes. Hopefully you're not smoking. Not good for you, you know. That is my public service announcement for today. But butane, you're thinking, now wait a minute. Butane in a lighter is a liquid. Well, yes, it is. But you know what? That container, that lighter, is pressurized. The pressure inside that butane lighter is quite a bit higher than standard pressure, right? And so that increase in pressure pushes those butane particles closer together, and they liquefy. But you know, when you depress the little button there, and don't press the flint to light it, but just depress the button. What comes out of there? It's not butane liquid. It's butane gas. All right. You can hear it. You can smell it. All right. So the only reason it's a liquid in a lighter is because it's under pressure. All right. Plus oxygen, which is O2, diatomic element gas, produces CO2, carbon dioxide gas, and water. Water a liquid here? Think about it. What do you use the butane lighter for? It's to set something on fire, to heat it up, right? This is a combustion reaction. A hydrocarbon ignited in the presence of O2 yields CO2 gas and H2O gas, right? Gas. Don't forget that. Remember that, all right? H2O is a gas in a combustion reaction. All right, let's balance this and we're done. 4 C's there. Put a 4 in front of CO2. 10 H's there. Let's put a 5 in front of water. Now we got O's left. Here we have 4 times 2 is 8. Plus 5 is 13. Uh-oh. That's an odd number. No can do. We balance with whole number coefficients. So if we have an odd number, how do we get rid of it? We multiply it by 2. So the 5 becomes 10. The 4 becomes 8. The C4H10 becomes 2. So our C's and our H's are still balanced. 8 C's, 8 C's, 20 H's, 20 H's. Now we can balance O because it'll be even. 10 there is 10. 8 times 2 is 16 is 26. What's going to go in front of the O2 to make it 26? And that would be 13. All right. You'll run into that a lot sometimes, especially on combustion reactions. All right. Well, we went over a lot today. A lot. So this balance in equations thing is maybe a little bit more involved than you remember it from back in the 7th grade, or even remember it from back in Chem 1, or some earlier class you've taken where you did this. So we got a little bit more to deal with now. So make sure that you're covering all the bases when you are doing these on your homework. All right. So the homework that you picked up today, that is due tomorrow. I'll be collecting that sucker. Believe me. We need to get going on this balancing, and you need to get good at it in a hurry. All right, in a hurry. So I think that's it for today. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard. Stay focused. We're in the home stretch, all right, of semester one. Stick with me, folks. We're almost there. We're almost there. Take care, everyone. See ya.